So what we're going to be looking at is finishing up section 3.1 and then looking at section 3.2. Now, what we looked at 3.1 was systems of equations. And we looked at one method for solving them was graphing them. Now, the kinds of equations we're looking at are what are called linear equations. It's where each equation represents a line. So what we do to find the solution by graphing them is we graph the two lines. And we can graph them using, say, x, y intercepts. You could graph them by putting them in y equals mx plus b or slope-intercept form. And then if the lines cross, the point where they cross, that's the solution. We're looking for a point xy that's shared by both of those lines, or put another way, a point xy that satisfies both of those lines. Now, there's three possible outcomes we could get. We hopefully and typically will get where they cross at one point. And that point's going to be the solution. The other possibility is that the two equations actually represent the same line. A common example of this is you take the same equation as a copy and then multiply this copy by, say, 3. Multiply both sides by 3. And so they'll represent the same line is what actually happens. And when you try to graph these lines, you'll graph one on top of the other. Well, that means they're constantly intersecting. So that means every single point that's shared by all those points in those lines, they're sharing those points. And that means all those points are solutions. So you can have the one solution where they cross. You can have one on top of the other. And all the points that are making up those two lines, they're all shared points. So you have infinitely many solutions made up of the points that make up the two lines. Again, only the points that make up the two lines. Finally, you can have parallel lines where they don't intersect, they're not contacting each other at all. And that means because there's no points that they share, there's no solution. And so you have a situation where you have two lines, they're different lines, but they're going to have the same slope. And so since there are no points in common, that means there are no solutions in that case. So that's how we look at things graphically. What we want to do now is try to solve for these solutions, whether we have one solution or infinitely many solutions, or we discover we don't have any. Can we do this without graphing? Because graphing can be kind of a clumsy thing. You've seen me try to do it. And it's oftentimes nicer if we can do it just using algebra. So we're going to try to just use algebra today. And we'll look at two methods. The first method was called substitution. So substitution is going to work like this. I'm going to go from example 3 in the text. So we have two lines here. Now one's already in y equals mx plus b form. This one is what we call standard form. Ax plus by equals c, where a is 7, b is -2, and c is going to be 3. And these are lines. You have just the x and the y. You don't have any x squareds or, say, square root of x or anything like that. And we want to figure out if these lines have a solution. In other words, is there a point that they both share? So with substitution, we're going to use this idea. An equation with one variable can be solved. So what does that mean? Well, if we look at these two equations, they have two variables. So this one, for example, is already solved for y. So technically, I guess you could say it has been solved. But we have y as an expression in terms of x. We want what we mean when we solved equations before, where we get a variable equal to a number. And so when we have two variables in an equation, we want to find a way to replace one of them with an expression using the other variable. Let me show. So I have an x and a y right here. If we could replace y with some expression in terms of x, well, then we'll have all x's in this equation. And then we can just solve for x using the skills we have for solving for x. The problem is, how do we replace y with an expression using only x in it? Well, we need a little bit of guidance on this, and fortunately we have some. To solve this system, what this says is we assume we're going to assume there's a solution, x comma y. So what that means is that x and y are shared by both equations. So when we're talking about the solution xy, well, if x comma y is a solution, then the y, for example, will work here, and the x will work here, but they will also work here as well. So if y is one of the solutions, then we're going to be talking about the same y in this case. In other words, where these two lines, if they do cross each other, they'll cross each other at the same point, xy. So that assumption allows us to assume, that assumption allows us to say that at that point where there's a solution, these are the same y's and these are the same x's. Now, this is really helpful. We can replace this y with minus 2x plus 4. The reason being, again, where these lines are crossed, and we assume that they do, we'll find out if that assumption works, is same xy in both equations, if that is a solution. Well, y has an alternative identity in terms of x. So we can replace y with this. And this is what's called substitution. So now we just got to solve for x. So to remove parentheses, I've got to distribute my -2. So -2 times -2 is +4. -2 times 4 is -8. Combine like terms. divide by 11. And so we get x is equal to 1. So we found half the solution so far, x is equal to 1. Well, let's see if we can find y here. Now to solve for y, or to find the value of y, we can choose any of the other two equations. So we're going to replace x with 1. And we can use any of the two equations. Now I'm going to go with the one that's kind of, I think, easiest to work with, the one that already has a y solved for, but it's in terms of x. So it's an equation just waiting for a value to be substituted in for x. So we have plus 4. So y is solved for. I mean, y is by itself, but we didn't get a number here. We like getting a number. We could get a number if we have a value for x, but we do have a value for x. We found out x was 1. So we substitute x is 1 and we find out y is equal to 2. So for our answer, what have we found? We found the point where these two lines intersect. Let's see. I'm not sure how accurate this line is. Let me see if they give a picture ahead of time. We'll have to, let me take a look at this. I want to give you a slightly accurate one, if I can help it. So it looks like it's doing this actually. It's doing. I can see. So I just want to give you a slightly accurate one if I can help this. Oh no, that's fine. So yeah, that looks good. So what we have is this. Oh. So where these two lines cross is the point, exactly the point, 1, 2. And so that's what we figured out. So without having to graph these, we were able to discover that one point that they share in common, and that's x equals 1, y equals 2. Questions about that? Let me see. Let me take a look at the homework problem. There's one particular type of problem they have. Just want to see if they're going to have you do it. So let's say you have this. Now, let's say you're going to solve this using the substitution method. I'm going to grab a different pen. In this case, we need to first solve for one of these variables. So let's do that first. So I'm going to solve using an equation that I think is easiest to work with. And what I'm looking ahead is I've got a y like this. Now, what I could do is I could add this to the other side and then subtract this over to this side, and I'm going to have y solved for. These other terms, you have to divide by something, and you have to divide, well, the entire equation. Say we're working with this y. We have to divide by 5. So divided by 5, divided by 5, divided by 5. We're going to get a bunch of fractions. And fractions are kind of maybe a little tiresome. But if we solve for y here, well, that's easier to solve for y. So we want to solve for one of the variables first. Could have been x, but y just seemed easiest. Then we're going to take this, we're going to substitute for y in the other equation. Now, this is where you do have to go to the other equation. If we were to substitute back into this, what we would ultimately get, so let's see, we would get 11 is equal to 11 is what's going to happen. So if we solve for y in this equation, we need the substitute into this equation. Replace this with our expression. So we'll start out with our equation as it is. Now we'll make our substitution. You can distribute the files. Combine like terms. And if I'm going too fast, let me know. And now we're just going to solve for x. I'm just going to rewrite my equation up here. Divide by 17. And we get x is equal to 3. So we solved for y, and then what we solved for, we substituted into the other equation. Now, when we have a number for x, again, x and y, if we have a solution, it's a point that's shared by both equations. That means the x will work for this equation, it'll also work for this equation. Or it'll also work for the equation we solved for. We can still use this one too. So I'll just substitute x with 3. And so we get x is negative 2. And that's going to be your answer. So any questions about that? All right, so that's the substitution method. The last method they talk about is called the addition method, or you can sometimes call it the elimination method. And the idea here, instead of solving for a variable and then substituting, what we're going to do is actually make a variable disappear by creating the third equation. So we're going to call this the addition method. So I'm going to take an idea. So I have two equations, and they're, I guess, kind of obvious. Let me make them less obvious. Let's say this is 4 plus 1. And this is 2 plus 1. Because 4 plus 1 gives you 5. 2 plus 1 gives you 3. Now what I'm going to do, I'm going to add the sides of these equations together. So I'm going to add this side, the left sides together. And I'm going to add the right sides together. Now, is this okay? Well, actually it is. 5 plus 2 plus 1 is 8. 4 plus 1 plus 3 is 8. So we can add the left side, we can add the right sides, and we're still going to have equality. You could sort of think of it as taking two scales, balanced, let's say 5-pound weights and balanced 3-pound weights, and just take the 3-pound weights, move them onto the 5-pound weights. You have 8 pounds on each side. So you can do that. If you take left side to left, right side to right, that'll work. So we're going to do the same thing with equations involving variables. So for example, so we have a first equation, and we have a second equation. Now these are not multiplied. This is just equation 1. This is labeling equation 2. In fact, well, I guess I'll just leave it like that. So we can add, say, left side to left side, and right side to right side. If we combine like terms, and since there's no operations we can complete inside the parentheses, this is as far as we can go. But if we combine like terms, and this would give us a third equation. So we can create these equations this way. If we wanted to, we could have done this. We could have taken 6x plus y equals 7, and then have y equals 2x plus 3, and then add these together. And then combine like terms. And that would also give us a third equation. So this is kind of a neat trick. The only thing we have to be careful of, once we decide which is the left side, which is the right side, we only want to add one side to one side, one side to one side. In other words, if we add y to this, we can't add this side to this. Can't do any cross adding. That's what we got to avoid. But questions about that? So how does this help us solve for anything? Well, we want to look for terms that cancel out. So, for example, and this is the one I'm going to use for the text. Let's give you a second to update your notes. So let's say we have this system of equations. Well, if we add right sides, we'll get 11 plus -7, that comes out to 4. Now, if we add the left sides, when we combine the like terms, the x's are going to cancel. And so that'll give us a third equation that only has the variable y. And when you have an equation with one variable, you can solve for that variable. And if there's a solution, you can get a number, hopefully. So let's do this. So if we combine like terms, we're going to have those 3's, x's cancel. This will go, and that'll go. And then -4 plus 2, well, that's going to give us -2y equals 4. Now we can solve for y. And we get y is -2. So that gives us y. Now we got to find x. And again, we're assuming that we're chasing after a solution, a point that's shared by these two lines. So that means y -2, that should work for both equations. So let's pick this one. Two times -2 is -4. And then we solve for x. So we're going to get x is equal to 1. So for our solution, we get 1 -2. So any questions about that? Now, there's a couple sort of tricky ones they'll throw at you here. Let's see. Because sometimes they don't cancel automatically. So if we add the left sides together, we're not going to get cancellation. So sometimes we have to do a little extra to cause cancellation to happen. So what we could do is this. sometimes we have to multiply through by a constant to create a situation where cancellation will occur. So let's say we want the x to cancel. We've got a 4x. Now if we add x and 4x, we're going to get 5x. We don't want that if we want x's to cancel. But if this was negative 4x and 4x, they're going to cancel. So what we're going to do is this. We're going to multiply the entire first equation by negative 4. Or put another way, and this is probably a more accurate way of putting it, we'll multiply both sides by negative 4. So we'll distribute here. And this is the key distribution we're looking for. This will give us negative 4x minus 12y equals negative 8. And now, with this new equation, we can replace this equation with this one. Now we can add both sides. I'm going to leave the parentheses off. We really don't need to have those there. I mean, you could have them there if you want. Again, combine like terms, and sure enough, those are going to cancel. Divide both sides by negative 7. That gives us y equals 1. So with y is equal to 1, we can substitute y is 1 into either the equations or the original one that we were working with. And we'll get an answer for x if we solve for x. So let's go with this equation. We could use this one, or we could use the other one that was x plus 3y equals 2. That one's probably easier to work with, but I'll stick with this one. But any of these three equations will work. And so we get x is equal to negative 1. So we get x is negative 1 and y is 1. Questions about that? There's one other type of problem. We probably won't get through 3.2 today because there are a number of problems there that take some time. But there's one other type of problem that I want to work with from this section. Let me see if they have it here. Oh, there's a good one. So let's say you've got this. So let's say this is your system. Now, you could use fractions here if you wanted to. Like if you multiply this by negative 5/2 and multiply everything through by negative 5/2 in this first equation, you could get negative 5 and 5, they would cancel. But you're going to get some messy fractions over here. So sometimes you want to multiply both equations by different numbers that will force a cancellation. So let's say we want to cancel the y's. Well, what if we turn 4 into positive 12 and negative 3 in the negative 12? Let's say we want to do that. Then, when we add these equations, we add the left sides, the negative 12 and 12 will cancel, eliminating the y's. So how do we turn negative 3 into negative 12? Well, we multiply by 4. And then the turn 4 in the 12, we multiply by 3. Just make sure I didn't skip anything. Okay, looks good. Sometimes you really want to give it a second look just to make sure you didn't leave anything out. So we're going to distribute. And now we can add the two sides. Again, negative 12y, 12y will cancel. So we get 23x equals, and then 8 plus 153, 161. Let's see, 161 divided by 23. Use the calculator. We'll get 7. So x is going to be 7. And again, to find y, we can use the two equations that we started with, or we could use the two modified versions of those. Any of those 4 equations will work. So what I'm going to do, I'm going to use, say, this equation here, just because it's there, it's readily available on the dry erase board. So knowing that x is 7, divide by negative 12. There you go. Y is equal to 4. So for our solution, we get 7 and 4. So any questions about that? So that's 3.1, and those are all the different problems I wanted to go over in that section. We'll probably have time to maybe do one question from 3.2. And the reason is there's story problems. And story problems, with those, we do want to take a little bit of time sort of looking at the setup. And there's a little bit of outside science that goes with some of these. So we'll finish 3.2 on Thursday, but we have enough time to at least do one problem. And a problem, it's a pretty good one, I think sort of practical, is example 3, the mixture problem. So let's see. Oh, this is very topical, given that we're going through the flu season right now. A chemist is working on a flu vaccine that needs to mix a 10% sodium iodine solution with a 60% sodium iodine solution. Let's see, sodium iodine. I think that's the chemical symbol for sodium iodine. Let me double check. Pardon me 1 second. Looks correct. So this is sodium iodide. That is sodium iodine. Double check real quick. Well, I'm going to not offend any future chemists, we're going to mix 10% sodium iodine solution with 60% sodium iodine solution to get $50 milliliters of 30%. So we're going to mix a 10% solution with a 60% solution to get a 30% solution. So here's going to be the question we're going to try to answer. So how much of the 10% and the 60% solution should we use? Now you can kind of think of this, I mean, this is for a flu shot, but you could think of this if you're mixing drinks, for example, like you have one proof alcohol, another proof alcohol, you want to get a proof that's in the middle, something like that. So this actually could be, depending on what kind of work you might find yourself doing, if you're doing anything with drink mixing, if you're doing anything, say, like any chemistry, really, and that's, you're dealing with drink mixing, that's really what you're dealing with. This kind of thing can come up. So let's break this down. So what we're going to do, what do we know? Well, we have a 10%. Let me start this off correctly. So we know we have a 10% solution. We have a 60% solution. And what we want is a 50 milliliters of a 30% solution. So what is it that we don't know? Well, there exists a 10% solution. There exists a 60% solution. We want 50, let me squeeze in milliliters there, 50 milliliters of 30% solution. Now, there's an inconsistency here. In fact, there's a couple. We have a quantity of the 30%. What about the quantity of 60? What about the quantity of 10%? So that's going to be our unknown. In fact, we have two unknowns. So with these solutions, we have two things, a quantity and a concentration. Quantity, concentration. But here we only have concentrations. We're missing the quantities. So let's let X be the amount of the 10% and Y the amount of the 60%. So, okay, that's great. Now let's think about some relationships. The final mixture, well, let's say that might be going a little bit too ahead. I want to show one relationship. And this is where you got to bring out a little bit of outside science. So the concentration is the amount of sodium iodine divided by the volume. Or what you could say, the amount of solution. So the amount of sodium iodine divided by the volume, or the amount of the solution. Now, oftentimes a solution, it's mostly water and then whatever you're mixing in. So, for example, and then this is kind of the outside science to bring in. Let's say we have 2 milliliters of sodium iodine dissolved in 8 milliliters of water. So what's the concentration? Well, it's the amount of sodium iodine divided by the total volume, which is 10 milliliters, the amount of water plus the amount of sodium iodide. And so that's going to give us 0.2. And let's see if you can see what I'm writing. I think you can. You're taking everything. If you can't see what I'm writing, let me know. Or 20%. So it's the amount of sodium iodine divided by the amount of solution. Now the solution is sodium iodine and, in this case, say water. So, and I'll just make a little note where that 10 comes from. 8 plus 2. So it looks like times. Fix that. So that's how I figure out the concentration. So given that, let's take a look at this. So if we want to figure out the amount of sodium iodine, abbreviating sodium iodine as sod iod. I hope that's okay. Well, what we're going to do is you take the amount of solution and you multiply by the concentration. So how does this work? Well, just real quickly, let's say we had our 10 milliliters. and we multiply by the concentration, 0.20, which is 20%. What we'll get is 2 milliliters of sodium iodide. So we can get the amount of sodium iodide back. We take the total volume of our solution, multiply by the concentration, percent, but turn that percent into a decimal, and that'll give us the amount of sodium iodide in that solution. So what we're going to get, there are going to be two expressions we're going to need, actually three. The amount of sodium iodide in the 10% solution was the amount of solution times the concentration of 10%, or 0.10. Now, we didn't know the amount of 10%, though. That's an x. So we'll express it like that. So we'll take the concentration, multiply by the amount, and that tells us how much sodium iodide is in this amount. Same thing for the 60%. Again, concentration times amount. 0.60 times the amount y, if we ever figure out how much that is. And then there's one last one. The amount of sodium iodine in the solution we're trying to come up with, the 50 milliliters. How much sodium iodide is in the 30% solution? Now this we can figure out because we were given an amount, 50 milliliters. What that is going to be. Come on, brain. There we go, 15. Doing math in your head is tricky. Sometimes better safe than sorry. So we do know the amount of sodium iodide in the 30% solution because we're given an amount of it. It's going to be 15 milliliters. So now we're going to construct our equations. Now they use a different system here. They use a box, which kind of helps. And so you can arrange this like so. Just checking on the time. We have time. So for the 10%, for the 60%, 30%. So we have the amount. Let's see. We have the percent. Percent concentration. And then we have the amount. Sodium iodide. So this isn't a bad tool to use at all. We have an amount, a percent concentration, and this is amount of solution. So that's the sodium iodine mixed in with, say, water. And then we have a percent concentration, and then we have the amount of sodium iodide. So for the 30%, it was 50 milliliters. The percent concentration, well, as a decimal, it's going to be 0.30. And then to find the amount of sodium iodide, we multiply these together, and we got 15 milliliters. Milliliters in there. Now for the other two, 0.60, 0.10. Well, we didn't have amounts of solution. That's what we're solving for. We called this one X. We called that one Y. Okay, fair enough. And the amount of sodium iodide, we find it the same way. Concentration times amount. So we can construct a chart like this that's going to help us for step 3. And here's why. Two unknowns means we need at least 2 equations. So 2 unknowns require at least 2 equations. So how do we come up with these 2 equations? Well, we need 2 equations that contain X and Y. Well, this is what we've got. If we take the amount of solution for 10%, add it to the amount of solution for 60, the total should be 50. So that will give us the total amount of our solution. And then we can look at the total amount of sodium iodide. Because again, this is going to become some amount in milliliters. This will become some amount in milliliters. And so this amount plus this amount should equal that amount, the total amount in the solution at the end. So that's going to give us our second equation. So we have one for quantity of solution. And that's going to be X plus Y is 50 milliliters. And then we can get a second equation for the quantity of sodium iodide. This will be 0.10x plus 0.60y equals 15. And that's going to be the system of equations we're going to solve. So let me solve this real quick, and then that'll be it for today. Any questions about this? All right. So We could use substitution. We could use addition. I'm going to use addition. I'm going to multiply through by negative 0.10. Distribute the negative 0.10. Or this will become negative. Negative 5. And now we have the other equation. If I add those sides, if I add these two sides, what I'm going to get, this is sort of a shortcut way of expressing it. Those will cancel. Negative 0.10, 0.6. We'll get negative 5 plus 15 is 10. Then divide both sides. 0.5 or 0.50. We'll get y is 20 milliliters. So what we discovered that we need 20 milliliters of the 60%. Now let's solve this for x. I'm going to use the easy equation. X plus y is 50. So you get x is 30 milliliters. So how much of a 10% solution and how much of a 60% solution need to be mixed together? So we have 50 milliliters of a 30% solution. Well, we need 30 milliliters of the 10%, 20 milliliters of the 60%, and we're good. And then we would check this, see if it makes sense. And I'm going to, steps 5 and 6, I'm going to skip those for the sake of time in terms of like, does this seem like a reasonable answer? And it kind of does. If we're picking a concentration between 60 and 10, it seems reasonable that we would have more, or maybe it makes sense to have more of the 10% than the 60%, but not necessarily. If you wanted, say, like a 58% solution, then you would probably mix more of the 60% solution than the 10%. But I mean, we're kind of going 30, kind of in the middle. So maybe this seems to kind of make sense. But that's going to be your answer. So that's it for 3.2 for today. We'll finish it up on Thursday. And if any questions, let me know. And again, the homework's not due tonight. It's due Thursday. And I'll try to get this posted ASAP. And then don't forget, finish your exam tonight. And other than that, have a wonderful evening.
Thank you. Have a good day.
No problem. Have a good day.